Alright, let's talk about the 2D gel electrophoresis. This is a common technique that's being used for the biology or the biochemistry people. So let's go over that one quickly. So when I say 2D, that means it just has the two separation stages. The first one is the isoelectronic separations. What it means is that they look for the pH, that's the whatever the molecule becomes neutral in certain pH. That's called isoelectric point. And then the second one is that you do use this SDS to actually make the protein negative, and then that they actually migrate under the applied electric field, and then you can actually measure the approximate size or the mass of the proteins or the large molecule. So let's go over the isoelectric point first. So each protein actually have its own isoelectric point, and the isoelectric point is neutral on average. So whatever the population of the protein you have, that certain protein, okay, one type of protein has on average it's going to be neutral. That's the isoelectric point really means. And each protein have its unique pH that associate with isoelectric point. So let's take a look at the polyprotic acid, which is some sort of a protein right here. So they have this H3, I think it's lysine 2+, and then H2 lysine plus, and then H lysine, and then lysine minus, right? So out of this, right, you're looking for the average point where the average charge of this protein that makes this protein completely neutral. When I say completely neutral, it's not really true. I think some of those, some percent stays positive, some percent become negative, but let's just try to look at this one right here. So that curve right here is the population of the 2+ protein right here, and that curve right here corresponds to the one positive charge, and then that green one represents the population of the neutral proteins, and then that one right here is the negative, and of course the x-axis being the pH, right? So for this particular case, the isoelectric point is probably somewhere around here. You see that it's mostly neutral, and then you have probably an equal amount of positive charge and negative charge here. So that's where the isoelectric point is. So just to keep in mind that even if it's isoelectric point, there are some positive charge and negative charge. What it just means is that on average it's neutral. Okay, you can never make everything goes to neutral. Okay, that's just how it is. Let me just copy that one. Let's look for the isoelectric point for this guy right here. Can you figure out where the isoelectric point is for this one? Alright, this is a 2+ ion. This is a single positive charge. That's neutral. And then this is going to be the negative charge, right? So where's the isoelectric point is? Isoelectric point is right here. Oh, I pressed it in the right place. Yeah, that's where it is. So about 95% of the things is neutral, and then maybe 2.5% positive charge, and then 2.5% negative charge. So how does the isoelectric point works? Isoelectric focusing works is that you have this gel, a certain type of gel, right? And then that on this plate right here, you have a varying pH. So somewhere around here, it's really basic. It's the pH of 13 or the pH of 14, somewhere around here, right? And then somewhere around here, it's pH of 1, so it's super acidic around here. When the surrounding portion is acidic, the ion tend to become positively charged, right? And then when the surrounding is high pH, where the surrounding is basic, then it tends to have the negative charge, right? So when the most of these guys are positive charge and then most of these guys are negative charge, right? So you're going to apply the gentle electric field, one side positive, the acidic side being positive and then the basic side negative. Then what happens is that negative charge is going to migrate this way because they don't like the negative charge. And then the positive charge, one of these guys, tend to move that way because they don't like the positive charge. So it migrates, and then when it's migrate, let's just focus on this highly positive protein right here, right? When it migrates, it starts to get this negative charge. At some point of some part of the protein has the specific pKa's, right? And that depends on the pKa values. It may actually become negative charge, the partially negative, or it may become partially positive, right? So as it moves from the left to right here, it becomes less and less positive. And then for the base part, it moves to the left, and then as it moves, it becomes less negative. And then at certain point, it stops moving because that it becomes a net neutral charge, and then that net neutral charge, it doesn't care what the applied electric fields are, so it stops moving, and that's the isoelectric separation is. So this is they call it as a isoelectric focusing, but that's pretty much how it works. It separates the proteins depends on its isoelectric point. So that's the first property of the protein that you can actually identify. Now let's move on to the second portion. Now the second portion is actually the gel electrophoresis, and then this stage the pH is constant. Usually we use buffer to keep everything constant. And then for this particular case, it's not the pH that separates, but it's actually separating the fragment by electric field and friction coefficient. Protein drift with the velocities of the v right here, which is called the drift velocities, is given by mu e. E is the electric field, and then mu is the mobility constant. And the mobility constant can be calculated by this formula right here. You may actually see this one right here. You probably have seen this one in the lecture 2.0, I think. That's the Stokes equation, right? That's a spherical particles drag coefficient, right? So that's the friction that's slowing down the movement, and then the top portion is the electric charge. Higher the electric charge that protein have, it feels a larger force, and then that it moves inside of this gel. So what is this SDS page stands for? That SDS stands for the sodium dodecasyl sulfate, which looks like this. And you have this unperturbed protein, right? The regular protein. But when you actually put the protein into the solution that contains this type of things, then what happens is that protein is going to stretch out. So this is like a polar portion and non-polar portion, which is going to stick very well with the protein. And then because of it carries a negative charge and negative charge repel each other, and then it's going to stretch out. So all the protein become stretched out like this rod right here, and it carries a large negative charge right here. And it depends, the number of charges, by the way, it depends on the size, right? Because if you have more lengths to it, then you will carry a lot more negative charges. If it's short right here, then only the negative charge you may actually find is very small. But when the protein is really large, then you carry a lot more negative charges here. And that's what the SDS really does. And the page stands for the polyacrylamide gel electrophoresis. It's just a gel. Right? And then that you do the electrophoresis inside of this gel right here. So what's the situation that we have for the second stage of the electric 2D gel electrophoresis? The charge will be distributed uniformly. That's coming from this guy right here. And the charge on the rod is nearly proportional, which means that the mass to charge ratio is pretty much constant, given that the size of the rod right here is uniform, meaning that no matter what protein you get, it's the rod size is not going to be thick or the narrow, right? It's not going to be like that, right? It's mostly uniform. So we ignore the radius of the rod right here. You just care about the rod length. Then in that case, mz is constant. M over z is constant. The mass divided by charge is constant because it's uniformly distributed. This negative charge is uniformly distributed. As the longer rod has a large mass, you divide by this charge numbers, then that should be equal to the short rod, the small mass, divided by the small number of charges that's associated with that. So it's going to be constant. So what's wrong with that one is that what we want is try to separate, right? But the problem is that the energy unit, which is a charge multiplied by the electric field change, or the voltage difference, right? Voltage difference multiplied by the charge should be equal to the kinetic energies for this particular case, which is 1/2 mv square, which you can actually solve for the velocities, right? But mass to charge ratio, right? Mass and the charge, they both grows as the rod gets longer and longer, right? So you're gonna get the same velocities. That's not good because you can't separate that, not from this equation right here. But luckily for us that we are not incorporating the friction right here. So when you start thinking about frictions, let's just assume that we have a spherical particle, which is certainly not the case, right? Because we know that it's a rod, right? Rod-like structures. But anyway, that you're gonna actually relate that frictions of the rod going through the gel is somewhat related to the spherical particle frictions by alpha right here. So it could be 1/2 or it could be the 1/3, but it's all the particle that's having the same rod shape, it's going to have the constant factor that coming from the spherical particle conversion of the spherical to rod-like particle. So maybe that this may be the movement of this rod right here has a friction that may have when I actually fold these things into the ball right here, that has a friction of the 6 pi 8r, but when you actually change that to the rod, I just need to multiply by that 6 pi 8r by maybe factor of 1.2 or 1.5 or something like that. That's the conversion factors of the friction coefficient. And then easy portion is that determines the force or the force that's applied on that particle, right? Depends on the voltage difference. So that whole thing is going to go into this mu right here, and then multiply by the applied electric field, which you can calculate that voltage difference between those two electrodes divided by the distance. You can actually get this E, and then multiply by mu, you can actually get the speed, particle speed.